Hi, everyone. So we continue to discuss logistic regression. So the next section is inference. So we discussed the testing in the first two videos. So we start with a general theorem in statistics, then we apply that theorem for logistic regression. So basically we want to thing to the F-test in linear model. So we would like to see that whether one model is significantly better than another model. Okay, so theorem 1, general theorem, the asymptotic distribution of a likelihood ratio. So suppose that we have a smaller model S and the larger model L, which nests S, and that model has L parameters. So here the L nests S, that means the L include all possible models in S. So for example, S is this model and L is this model. So in two parameters, beta naught and beta 1, L has 3 parameters, beta naught, beta 1, and beta 2. So L minus S is 1, and here the difference theta. So parameter theta is beta 2. So theta represents difference between S and L. Then further, let LS and LL be the estimated log likelihood function of the two models. So actually the larger model always has larger likelihood. So LL is always larger than LS. So log of LS over LL is negative. So if we multiply by -2, that is always positive number. And that actually converges to chi-square distribution with degrees of freedom L minus S as n goes to infinity. Yeah. So the chi-square distribution has the expectation equal to the degrees of freedom. So for example, if this chi-square L minus S is 2, then this test statistic converges to chi-square distribution with df2. So the graph looks like this. So if test statistic is very large, around here, then that means the difference between LS and LL is larger. So that means the model L is significantly better than model S. So this works in any statistical model, but we use this result to logistic regression. Okay, so at first we define the deviance. So given a logistic regression model, the deviance D is defined by this. So basically, this is the likelihood ratio. But we compare the likelihood ratio with some baseline. And the baseline is actually the perfect model. So we see whether, how close our model is compared to the perfect model. So it's similar to the idea of the residuals in linear regression. So if residual is 0, then that is a perfect model. If residual is somewhat different from 0, then the model is not perfect. So we measure the distance from the perfect. So we are the same thing. So we have the same thing here. L and L infinity are the same, then D becomes 0. So it's similar quantity as residual. And from the likelihood function of regression, E is equal to this quantity. And also we define the null deviance D naught. This is the deviance for the null model. So just eta is equal to beta naught. So remember that eta is fitted value of the regression. So eta is equal to beta naught plus beta 1x1 plus up to beta qxq in logistic regression. And e to the power eta over e1 plus e to the power eta. So this is equal to fitted probability. So this is y. That is probability of y is equal to 1. Yeah. Okay, so with this notation, we can construct a test. So to test H0 against H1. So here that we compare the baseline, so just nothing. So the eta is equal to constant against this alternative. So this is usual logistic regression. So we want to see if logistic regression is at least meaningful compared to no information. So H0 is theta is equal to 0. So that is the null model, eta. And the alternative is theta is not equal to 0. So that is actually H1 is better. Actually, this is H1, this model. Okay, then use the theorem that we discussed just a few minutes ago. Then D0 minus D follows chi-square distribution with DFQ because we have Q additional parameters in H1. And so we can test D0 minus D. So reject H0 if D0 minus D is larger than some threshold. So that is, okay, so we have chi-square distribution. So chi-square distribution with DFQ. This is density function, and our test statistic is here. Then if test statistic fall in this area is larger than some alpha that is significance level, then we reject null hypothesis. So if, for example, this area, if this area is 5%, maybe in general alpha, then if our test statistic is larger than this chi-square Q of alpha, then we reject null hypothesis. So if test statistic right-hand side of this threshold, then we reject null hypothesis. So this is the scheme. Okay, so now that we have an example, so remember that we regress the disease, the heart disease, the occurrence of heart disease, that is Y. So we fit, okay, so Y is, okay, transformed the inverse logit function of eta, and eta is equal to beta naught plus beta 1 x1 plus beta 2 x2. X1 was basically the occurrence of heart disease, and X1 is the height, and X2 is the number of cigarettes per day. So we have two parameters. So we want to compare this model with the null model, that is eta is equal to beta naught. So at first the null deviance and also the residual deviance, that is the deviance for this model. Then we get the 1781.2 and 1749. Is 2 because we have beta 1 and beta 2 here. So this difference, that is 32.2, follows chi-square distribution with DF2. And actually this number is pretty large because chi-square distribution of with DF2, that has the expectation of 2. 32.2 is much larger. So the situation is we have the chi-square distribution here. So 2 is the expectation, slightly larger than mode, but the 32 should be very large value, maybe around here. So p-value should be very small. And actually p-value is 10 to the power -7 almost. So it's very significant. So it's much smaller than, for example, 0.05. So we reject null hypothesis and we support the alternative that eta is explained by height and cigarette in some way. Okay, so this is the basic test for logistic regression.